So today we're going to have a look at an average rate of change. Now basically what does that mean? Well, it asks the question. Most things in life have a constant rate of change. For example, if you were to get fuel, the first litre you pay for, if it costs 1.30 cents per litre, well, the first litre and the 20th litre is going to cost you the same amount. It doesn't matter the fact that one's the first and one's the last. However, in other places, you're going to find that rates actually change, so we need to be able to average them. And the way we average them is we use the gradient formula. We find the change in one variable, and we divide it by the change in the other variable. Alrighty, we can also write this as the triangle symbol del y over del x, just meaning the change in y over the change in x. So let's have a look at an example. So on a hot, wet day, a wet woolen jumper is hung on a clothesline to dry. It is weighed every 10 minutes for half an hour. The mass is shown in the table below. All right, so we've got the time in minutes, 0, 10, 20, 30, and the mass in grams is 2,000, 1,500, 1,200, 1,000. So calculate the average rate of change of mass during the first 10 minutes. So what is it? Well, the mass has gone down 500 and the time's gone up by 10 minutes. So the average rate of change is going to be the change in the mass over the change in the time. So that's going to be 1,500 minus 2,000 over 10 minus 0. Well, negative 500 over 10, negative 50 grams per minute. The second part asks us, well, how much did it change over the first 30 minutes? So, for the average rate of change, well, once again, it's going to be the change in the mass, del mass over del time, the change in the time, which is going to be, well, at the end of 30 minutes, it's 1,000. So it's gone down by 1,000 minus 1,000. So 1,000 minus 2,000. And the time is 30 minus 0, which is 30. And we get negative 1,000 over 30, which is negative 100 over 3, which is approximately negative 33.33 grams per minute. So you might ask the question, well, as the question does, why was it different? Well, if you have a look at the amount, it's not going down by a consistent amount. In the first, it's going down by 500, then it's going down by 300, then it's going down by 200. And the reason this might be is that it's slowly going to approach the actual mass of a jumper. Right, so at the beginning there's lots of water, so some of it's dripping out, a lot of it's just seeping off. It's still pretty cold because it just came straight out, but over time it's going to slowly warm up, and eventually some of that moisture left in it, some of that mass in the form of water, is going to begin to evaporate. But it takes longer and longer the smaller amounts there is left. And there's also less of it, so there's not as much of it to leave. So you can see the power of doing an average rate of change rather than an absolute. Alrighty, so let's have a look at doing this. So now we're going to do it via a graph. So the graph of an object, the following graph shows the distance traveled by an object. Use the graph to complete the table of values. So at 0, it's traveled 0. At 1, it's traveled 300, 500, 600. At 5, it's 700. It's not going up linearly. At 9, we get to 800, and at 10, we get to 1,000. Calculate the average speed of the object. Well, the average speed would be over the whole thing, and we could actually just have a look by connecting the beginning to the end, and we'd see that it almost perfectly matches. In fact, it does perfectly match up. That in 10 hours, we've gone 1,000. So, for part B, the average speed of the object, well, that's the average rate of change. For speed is a rate of change. Well, that's the difference in the distance del distance over del time, which is 1,000 over 10, which is 100 kilometers per hour. Because in 1,000 kilometers, in 10 hours, we've gone 1,000 kilometers. Right, but as we notice, the graph doesn't actually have a slope of 100. In fact, at the beginning, it has a steeper slope, then it kind of shallows out until it gets really quite shallow by around the 5-6 month. You're not really going anywhere. In fact, you can even think you might be cruising on by, not going that far at all. And then right near the end, we steepen back up and get a little bit just before home. All right, so you can see that although the average speed of the object is 100 kilometers per hour, in fact, we're not actually going at 100 kilometers per hour for really any part of the journey. It's just in the average. In fact, the only place we're really going about 100 kilometers per hour is about over here, where the slope sort of matches there. Alrighty, so calculate the average speed of the object from the end of the first hour to the end of the 9th hour. So end of the first hour to the end of the 9th hour. So let's have a look at that. Well, the end of the first hour, we've travelled 300. So let's have a look. Average speed. Del dist over del time. The change in distance. Well, we're going to end at 800 meters. And we've travelled 300 meters. And 9 minus 1. And so we get 500 over 8, which is 62.5 kilometers per hour. So once again, we can see that the average does not tell us the whole story, because for 8 of the hours, we're only going at about 62 kilometers per hour. However, for those other 2 hours, we are blitzing through it and traveling, well, I mean, you can have a look here. We travelled 300 kilometers in the first hour. That's 300 kilometers per hour. That's quite quick. Hopefully this isn't a car. Otherwise, probably a bit dangerous. The last example is going to be looking at how we can actually use these average rates of change. All right, the first thing we're going to do is draw a graph. So let's quickly go through that. There's my x-axis. Alrighty, so we got the population versus the time in years. Alright, so let's plot some points. So alrighty, so we kind of get, I'm going to try to connect it all with a nice smooth shape, just like that. Alrighty, there we go. So there is my completed graph showing the population of the foxes over 4 years. So B, calculate the average decrease in the number of foxes over the first 2 years. B, average change of population. Well, it's the change in the population over the change in time. So the change in population over the first 2 years is that it goes to 200 starting from 800, and it's 2 minus 0. Negative 300, meaning losing 300 foxes per year. For part 2, we're looking for the total average change in the population. Alrighty, which is going to be del pop over the del in time. So it's 100 minus 800 over 4 years. 1 minus 175 foxes per year. So you can see that although in the instantaneous, over 2 years we've got one rate of change, over the 4 years we've got a different rate of change. And you can see that the blue line has a lower gradient than the other line. Now we call these lines secants, and a secant is a line that goes through 2 points on a curve. And the secant can kind of show us the gradient, or this rate of change, visually. For a linear line, the gradient is the rate of change. Alrighty. Hope you've had a bit of go with average rates of change.